Okay, can you guys read what's written on the whiteboard?
Yes.
So the picture is clear, right?
Yes,
Yes.
Dada.
Okay. I hope we don't have problems like the previous. Okay, so I guess we can start now. So yesterday we covered the addition principle, multiplication principle, a basic notion of what permutations and combinations are, and a brief foray into double counting. So, does anyone have any question on whatever's been taught till now?
Here, can you just re-explain the identity nc u square plus nc1 square to nc n square is equal to 2nc n?
Okay, we'll do that again when we revisit double counting. So, other than that,
Can you please explain the golden ratio?
Showing low bandwidth.
Cannot see the screen, it's loading.
Network issues.
now suppose we've been asked to find all numbers less than equal to 100, which is divisible by 2 or 3.
Please repeat from the start.
Okay, I'll repeat from the start. So, suppose we have two sets. This is the set of all
Switched
numbers
off.
of the form 2n.
Cannot see the video.
See the screen, your video is switched off.
Yeah, we cannot see the
Okay.
video.
I can't see the screen.
You can see now, I hope.
Yes, it's now visible.
Yeah.
Yes.
Okay, so we have two sets. One of them is numbers of the form 2n, and the other set is the number of are numbers of the form 3n. So suppose we have a problem which says we have to find all numbers from 1 to 100 which are divisible by 2 or 3. So you might think that
Is the answer 67?
we'll get to the answer later. So
Your video has gone off again.
Yes, sir. Your video is not.
Okay, just give me.
We cannot see you.
Okay, so you might think that the answer is
I love to
N.
eat pie.
Nice. Okay, so suppose you might think that the answer is n from 1 to 50 over here. So all numbers from 2, 4, 6, 8 up to 100. And you might think that n is from 1 to 33 over here. So 3, 6, 9 up to 99. So this gives our answer as 50 plus 33. That's 83. But the major mistake that we have made in this Venn diagram representation, can anyone tell me what that is? Okay, I'll just write this different
Not considering 0 or 1.
So,
0 and 1 are not divisible by 2 and 3 anyway. So we have numbers like 2, 4, 6 up to 100 here, and we have numbers 3, 9 up to 99 over here. So what's wrong with this Venn diagram representation?
Certain numbers have been double counted.
Overlapping.
Yeah, so what's wrong with this diagram?
0 divisible by 2. 2 into 0.
The intersection has not been drawn. Certain
Exactly.
numbers have been double counted.
Not been drawn, right?
there should be intersection.
So these two sets over here, we have represented them as disjoint sets. But see, we have 6 over here and we have 6 over here as well. So obviously these two have an intersection set. So if we draw this like this, it would be a more accurate representation. Okay, let's call this set 1 and call this set 2. Set 1 is all multiples of 2 and set 2 is all multiples of 3. So now we have an intersection set over here. Now, what exactly is this intersection set? Can anyone tell me?
Some multiples of 2 are also
Multiples of 6.
Multiple of 6.
Multiples of 6, exactly. So all numbers which are multiples of 2 and 3. So basically LCM of 2 and 3, which is 6. Multiples of 6. So when we got 83 as our answer, we counted all the multiples of 6 twice. We counted them in the set of all multiples of 2 and we again counted them in the set of all multiples of 3. So we need to subtract this from our original answer. So how many multiples of 6 do we have from 1 to 100? We have 16. So if we subtract 16 from here, we get our final answer as 67. Right? So yes, whoever said 67 was correct. Is this clear?
Why did you
board is
subtract 16?
What?
Subtracted 16. Can you tell why? From it.
Oh, we subtracted 16 because see, we counted the multiples of 6 twice, right? We counted them when we considered the set of all multiples of 2. Okay, so let me draw it like this. So we have multiples of 2 over here. So these are 2, 4, 6, 8, 10, 12. So when we are counting them, we are counting 6 over here, we are counting 12 over here. And when we are counting the multiples of 3, we again count 6 and 12. So basically the multiples of 6 are being counted twice. And hence we need to subtract all the numbers that we have over counted. So 16, hence we get 16. Because there are 16 multiples of 6 from 1 to 100. Okay?
Dada,
So we'll write this.
I did
Yeah.
understand why did you do 50 plus 30, that 33 wala part.
Okay, 50 plus 33. So how many multiples of 2 are there from 1 to 100?
Yeah, 50, 50.
50. And how many multiples of 3 do we have?
33. Acha, we multiply, we
33,
added
right.
that.
Yeah, we added them. But we overcounted the multiples of 6 and that's why we subtracted.
Okay.
So we'll write this more formally now. So do you guys have an idea of what intersection and union of sets are?
Yeah.
Okay, so we'll use that notation then. So suppose we have two sets A and B.
Somebody has started sharing a whiteboard.
Yes, somebody has
Multiply.
started.
Okay, could you please stop doing that?
Yeah, he stopped now.
Okay, cool. So we have set A and set B here, and this set, what we have filled with blue, this set is A intersection B. Now the number of distinct elements in A plus B. So the number of elements in both these sets, that is distinct elements, is A plus B minus A intersection B. Is this clear? I'll use this. This is just the number of elements in the set. So is the formal definition clear to you guys?
What does mod represent here?
So the number of elements in the set A.
But why are we doing it mod?
It's not mod like you have in algebra, like mod of -5 is 5. It's not like that. This is just a set theoretic notation, which denotes that the number of elements in A. So, so suppose in our previous example, take the set of multiples of 2 between 1 and 100. So if we consider that set to be S, then mod of S would be 50, because we have 50 such multiples. Okay, don't call it mod. Like, yeah.
Tell again. I did not understand.
Okay, so in our previous example, we considered, let S be the set of multiples of 2 between 1 and 100. So if we consider the mod S, it would be 50. So this mod represents the number of elements in the set.
Elements? 2.
Yeah. Were you saying anything?
I asked what are elements? Multiples of 2.
Yeah, multiples of 2.
The screen is getting very hazy. I cannot see what you have written, and I cannot even note it down.
Okay.
Bhaiya,
Is anyone else facing?
it's getting sometimes crazy, so we can't see what you have written.
Okay. Is it hazy now?
No, now it's not. It's get crazy, Madhva. Sometime.
It's for me still.
Okay, just let me know when it's hazy.
Okay.
Okay, maybe if it's hazy, sometimes the problem is on your end. Most of the times it will be on mine, because I have very poor net connection, but sometimes it's possible that your net connection is poor.
My net is okay. I don't think I have a problem on my side.
Okay, yeah, cool then. So we'll extend this for 3 elements. 3 elements, sorry, I mean 3 sets. So we consider a problem similar to our first one. So now consider this set A. A is all numbers multiples of 2 from 1 to 100 again. So we have 2, 4, 6 up to 100. Now set B is multiples of 3 from 1 to 100. So we have 3, 6, 9 up to 99. And we have set C, which is multiples of 5. So we have 5, 10, 15 up to 20, 100. So we have an intersection of all these 3 sets.
2, 3, and 5.
And 2, 3, and 5. Yeah, multiples. Okay, I'll write it a bit bigger. So these are multiples of 2. These are multiples of 3.
It will be like
These
this,
are
right?
multiples
A
of
plus
5.
B plus C minus AB minus BC minus CA plus ABC.
Yeah, exactly. So we consider the consider this similar to the first problem. We need to find all numbers from 1 to 100 which are divisible by 2, 3, or 5. So again, let's consider modulus of set A. That is all multiples of 2 from 1 to 100. This is obviously 50. Modulus of B is 33 and of C is 20. So if we add all of them, we get 103, and obviously that's not the answer because we have 100 numbers, right? So, okay. So if we add them, we get 103. Now, obviously we have overcounted some numbers again. We have overcounted multiples of 6 because, okay, see, element set A has elements 2, 4, 6, 8, 10, blah, blah, blah. B has 3, 6, 9, 12. Okay, we'll add 12 here as well. 15. And C has 5, 10, 15, 20. So we overcounted the multiples of 6 again. We counted 6 here, 12 here. We counted 6 and 12 here as well. So multiples of 6 are basically A intersection of B. So A intersection B, that is multiples of 6, we double counted. So that is 16. We also counted A intersection C. So what is that? LCM of 2 and 5, that is 10. So we counted 10 over here
Is this cracking?
and we counted 10 over here as well. Okay, can you see clearly now?
Your video has gone off.
Oh, it's gone off again.
But it is hazy.
Okay, so we were considering
Now
the
it's okay.
now it's okay.
It is
Okay, so we were considering the intersection set. Is it clear now?
hazy again. And your voice is also not coming sometimes.
Okay. I hope it's clearer now.
No, it is.
No, it's still very hazy.
Hazy.
Yeah, it is hazy.
Your voice is cracking.
Stop and
Here.
it's clear now?
Yeah.
Yeah, it's clear now.
Yeah, it's clear.
Okay. So we were considering the intersection of these sets. So we counted all the multiples of 6. We overcounted the multiples of 6 16 times. Now if we take A intersection of C, that is all multiples of 10, right? Because LCM of 2 and 5 is 10. So we counted 10 over
I
here.
cannot hear you.
Can the others hear me?
You.
Okay. So A intersection C is basically the multiples of 10. So we have 10 of those. And B intersection C, that is 3 and 5, the LCM is 15. So we have 6 elements there. So now if we subtract all these overcounted numbers from here, we get 103 minus 16 minus 10 minus 6, which gives us what, 71, I think. Okay, yeah, 71.
But the LCM of all of these three has also to be subtracted. Is
Exactly.
235. So the answer will be 68.
Yeah.
Please
So
speak slowly. It's hurting my ears.
okay, in these 16 numbers, so these are multiples of 6. These are of the form 6n. These are of the form 10n. And these are of the form 15n, I think. Yeah.
Ahir, can you explain again? I could not hear you.
Okay, we just basically did what we did in the first problem. So we subtracted all the intersections of pairwise intersection set. Like we took A intersection B, 16, A intersection C, multiples of 10, multiples of 10, and B intersection C, which is multiples of 15. And we subtracted that from our original answer. So now we have 71. But we have, so these are numbers of the form 6n, these are numbers of the form 10n, and these are numbers of the form 15n. Now if we take the LCM of these three, we get 30. So we've been subtracting.
Hello.
Yeah.
Yes, bhaiya, no offense, but there's a ID named Chobelal Torka Moshla. I don't think it's a real ID. You may ask them.
Acha, okay. So wherever you are, you get to comment on anything.
Yeah, it's Chobelal Torka Moshla.
Okay, it's fine. You can.
Creative he is, isn't it?
Yeah, so we have multiples of 6, we have multiples of 10, and we have multiples of 15. So these are 6, 12, 18, 24, 30. These are 10, 20, 30, 40, 50. And these are 15, 30, 45, 60. So once again, we are now we are subtracting extra. So all the multiples of 30, we have them, they're in the form of 6n, they're in the form of 10n, and they're also in the form of 15n. So we are over subtracting in this case. And hence, we also need to add the intersection of all these three, which gives us what? 3. So 71 plus 3 is 74. A intersection B intersection C is basically all the multiples of 30. Right. Now, if we took a general case of say n set,
Is the answer 4? Final answer.
a set 74, yes.
Yes, 74.
Yeah. So if we had n such sets, the number of distinct elements would be, let me just write this. For n set, the number of, suppose the sets are A1, A2, up to AN, then the number of distinct elements would be A1 plus A2 up to AN, minus the pairwise intersection of all these, A1 intersection A2, and we take all the pairwise combinations, plus intersection of 3 of these. So we take all such triples, and we keep on alternating the sign. So we subtract the 4 tuples of intersection A3, A4, and so on, alternating the sign. So you can prove this yourself if you want. I'll leave that for you. So now another very interesting problem solving technique that we get from this principle is called counting the complement. So, okay, counting the complement. So suppose this is the universal set. Now the universal set can be anything from the set of natural numbers to the set of 6-digit numbers. It depends on the problem. So suppose you have the universal set, and suppose A is your solution set. Now sometimes it's very complicated to find the number of elements in A, and that can be for various reasons. Or you might have multiple sets like A, B, C, and it's complicated finding all the distinct elements that you have here. So what you can do in that case is, if you know the number of elements in the universal set, and if you know the elements which are not in any of these sets, so basically this part, then you can take the universal set and you can subtract all the elements which are not in any of these sets. So if we call this S, then U minus S gives us our answer. We'll try to understand this with a problem. So find all 6-digit numbers which have at least one even digit. So I'll give you guys 2 minutes to solve this.
Is the answer 90,880?
90,880. Okay, we'll pause this.
90,000. And the number of odd digit numbers is 5 factorial. That is 90,000 minus 5 factorial. Is that the answer?
That's 125 factorial, and I think it will end up
89880.
Sorry. I got subtraction wrong. The final answer 89,880.
89,800. Okay, we'll solve this and see. So I'll let the others try for another minute and then we'll solve it. Okay, so we'll try solving this now. Is the whiteboard hazy to you guys, or can you are sitting on the board?
It is hazy a bit.
Okay, I'll just switch it off. What about now?
It is the same, means it is a bit hazy.
So can you at least read what's written on the board?
Some words are understandable, but some are not.
Okay, so
Most
I'll
of
just
them are not.
I'll write a bit bigger. So let's try to solve it. Now we have to find all 6-digit numbers which have at least one even digit in them. Now, so there are many cases over here. There could be one even digit, there could be two even digits, up to 6 even digits. So 6 separate cases and a lot of tedious calculation. So what we could do instead is find out So we have 5 to the power 6 as number. And how many 6-digit numbers do we have in total? 900,000. So our final answer is
Dada, your video has gone off.
it's gone off.
Yes.
Yes.
And now
Still off. Now it is loading. It is showing that due to low bandwidth, your video has stopped. It will resume when the conditions improve.
is everyone else facing this problem?
Yeah, it's showing here also.
Yes.
Okay, can you see it now?
Oh, it loaded for some for 1 or 2 seconds, then again the video went off. Yeah, now it is visible.
Okay, it's visible now, right? Yeah, I can see the chat. Am I audible to you guys?
Yes, yes.
Oh, okay, cool. Okay, so these, so 5 to the power 6 are all 6-digit numbers which have odd digits. And we had to find all numbers which had at least one even digit. So our answer is all 6-digit numbers minus these 5 to the power 6 numbers. So that gives us 900,000 minus 5 to the power 6. What's 5 to the power 6? It would be a 5, 25, 125, 125 into 125 would be what? 120, 15625. So we have 15625, and you can calculate this, but whatever it comes. So now we have enough knowledge to approach an RMO problem. Yeah, go ahead.
Someone has 8 identical pens. In how many ways can he select 2 pens? We did this sum in the last session, but the answer which came out was 28. But how it is 28? Because all of them are identical. So the number of ways in which we do select 2 pens does not depend, because all of them are looking the same.
It will be 8C2. That will be 8 into 7 by 2.
Okay, yeah. You've got a point.
All pens are identical, so that doesn't
Identical,
depend on the.
yeah. You have only one combination.
There could be only one combination.
Yeah. So all the pens have to be distinct for it to be 20. Yeah. Thanks for pointing that out.
Yes, I think enough people have joined. You can start.
Okay, yeah. So in the previous problem, we said 900,000 because that's the total number of six-digit numbers that we have. So it starts from what 100,000 to 999,999. So that's a total of 900,000 numbers, and that's why 900.
So, why did you find out?
You're breaking up a bit. Could you repeat?
To 6.
Could you just write it in the chat because you're breaking up? Okay, so 5 to the power 6. So what we had to find in this question was all the six-digit numbers which had at least one even digit. So if you consider the complement of that, complement is basically all the numbers here which are not satisfying this property. So that is all numbers which have odd digits at all the six places. So you could do that in, so you have five odd digits, right? You could have five in this, 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 and five in this. So that gives us 5 to the power 6. And you're choosing 5 from the set 1, 3, 5, 7, 9.
Say the odd numbers are repeatable.
Yeah, you could repeat them.
Oh, I didn't heard that. I thought they could not be repeated. That's
Oh
why
no, we are just,
it's factorial.
yeah, all 5-digit numbers, nah, 6-digit numbers, so you can repeat them.
Then it
So,
will be 90,000 minus 5 to the 6.
yeah, so it's 900,000 minus 5 to the power 6. 5 to the power 6 is what? 1, 5,
25 cubed, that's 625 into.
yeah, 15625.
To
So
5.
that's 900,000 minus 1565, yeah, whatever that comes. So we have enough knowledge to approach an RMO problem. I'll share the screen so you guys can. I hope you guys can. Give me a minute. Okay, can you guys read the question?
Yes.
Okay, cool. So I'll give you guys uh 2-3 minutes to try this.
28 into 24 into 20.
It's quite big. So it is coming as 28C3 minus 28 into 24 minus 14 into 22.
Is the answer 4422?
So should we start with the solution now, or do you guys need some more time?
Could you also teach some basics of the circle permutation combinations?
Yeah. We'll definitely do some problems on this. Okay, so we'll start solving this problem now.
Did you started explaining?
No, I'm starting now. So you guys can see the board?
No. Yeah, now you can see. Again it
Okay,
went
so
off.
we'll approach
Again it went off.
when it went off. Okay.
And now it's okay.
It's okay. Okay, so we'll approach this problem similar to the previous one. So we have 28 points like this. So let's say this is 1, 2, 3, and we go on till 28. So what's the total number of ways in which we can select 3 points?
Your video turned off.
Dada, again the screen is gone.
Okay.
Now it is okay.
Okay. So the number of
Yeah,
ways
it's
in which
okay.
we can select 3 points from 28 is obviously 28C3. We have to find all the ways in which we can select these 3 points such that no two of them are adjacent or diametrically opposite. So let's take the first case as all the 3 points are adjacent. So we can do this in 28 ways because see, you can select 1, 2, 3. You can select 2, 3, 4, 3, 4, 5, like that up to 28, 1, 2. So you have 28 ways of doing that. So we subtract 28 from 28C3. This is our first case. Now the second case is
From what did we subtract to 28?
We took the first case as all the numbers which all the points are adjacent. So like there are 3 consecutive points. 1, 2, 3,
No, I'm
2, 3,
talking
4, 3,
what's
4,
that
5.
2PC3?
Oh, this is 28C3. Sorry, I misread. So 28C3 is all the ways in which you can select 3 points from these 28. So that's 28C3. And 28 is the number of ways in which we can select 3 points which are adjacent. That means all the 3 points are adjacent, so consecutive. Now case 2 is 2 of the points are adjacent and the other point is not. So we can do this in, again, we can select in 28 ways. And now in how many ways can we select the other point?
28 way?
How is it 28? We are selecting
27. No. 26, right?
26, but we said that all the 3 points are not adjacent. The third point is not adjacent to these two. So it can be, so suppose we are selecting these 2 points. The point 3 cannot be over here or here. So we are excluding these 4 points.
Oh, that would make it 24, right?
24,
Got
yes.
it.
So that's our second case. And the third case is 2 of the points are diametrically opposite and the third point is not adjacent. Now we are not considering the third point to be adjacent because we have already counted them in the first 2 cases. So in a third case, 2 of the points are diametrically opposite and the third point is not adjacent to either of them. Now we could select 2 diametrically opposite points in 14 ways, right? So we can select 115, 216, 317 like that up to 1328, right?
Hello?
Yeah, 1327. Sorry, 1428. I think, right? We select 15 up to 1428. So in case C, we can select the diametrically opposite pairs in 14 ways. And again, how many ways could we choose the third one? So suppose this and this are diametrically opposite points. So the third point can be adjacent to this. So it can be over here or here, and it can be over here or here. So we have 1, 2, 3, 4, 5, 6 points where the third point cannot be. So we have 22 remaining points left. So basically it's 28 C3 minus 28 for all the 3 points adjacent, 28 into 24 for 2 points adjacent and the third one non-adjacent, and 14 into 22 for diametrically opposite points and the third one non-adjacent.
Dada, can you repeat the last one? 14 into 22.
14 into 22, sure. So in how many ways can we select 2 points which are diametrically opposite over here? So suppose this is 15. So we could select 1 and 15. We could select 2 and 16 up to 14 and 28. So we could do that in 14 ways. And now in how many ways could we select the third point? So suppose we chose 1 and 15 as our first 2 points. So the third point cannot be point number 2, point number 28, point number 14, or point number 16. And obviously it can be 1 and 15. So we cannot choose these 6 points. And we are left with 22. Hence 14 into 22. Is it clear to you guys now?
Yes, Bhaiya.
Yeah, so this is from RMO 2015, I think. It is simple problem actually. Takes 2 minutes to solve. We basically use the same technique over here in the counting the complement.
But just there were different compliments here.
Yeah, exactly. Okay, so let's check out another RMO problem. So okay, this one's slightly more tricky. You guys should be able to solve. It's not letting me share my screen for some reason, so I think I'll just write it on the whiteboard. You guys. Or okay, I'll just send it in the chat.
Bhaiya, are you speaking anything?
No, I'm lighting the problem for you.
But it's not visible.
No, I'm just writing it in the chat for you. I sent it in the chat. Can you guys see it? Okay, the message isn't going for some reason.
Yeah, we have not received it.
We did not receive it. Now we got it.
Okay. So I'll give you 3.2 minutes to try this. It's a pretty simple problem.
It's all up here.
Okay, so one of you already solved it with proper reasoning. So we'll start. So suppose you have, you guys can hear me, right?
Yes, yes.
Okay,
Yes,
okay,
Dia.
cool. So suppose you have n white points over here. So what is the maximum number of
Your video went off.
Dada, again off.
Hope it's on now.
Yes, but it's a bit.
Okay, we don't need the whiteboard marks for this problem actually. So suppose you have n white points in the plane, on the paper. Sorry. So what is the maximum number of red points that you can obtain from these n white points?
Could you please repeat?
It's 3.
Suppose we have n white points on the paper. What is the maximum number of red points that you can obtain from these white points?
And white.
3.
Could you repeat, please? It's breaking up.
N by
I guess. It's 3.
Yeah, it's NC3. So by the definition of a red point is the center of a circle which passes through 3 white points. So if we select any 3 of these n white points, then we could obtain a red point. So suppose white points, we have n. So max number of red points, is NC3. NC3. So that means our total number of points are n plus NC3. And since we have 100 such points, this has to be more than equal to 100. Now you can just simply put 9 over here and check. So if you put n equals 9, this is 9 plus 93, and 9 plus 93 is what, 84, I think. So 93 is 84, so we get 93, which is obviously less than 100. So let's try taking 10. So 10 plus 10c3, and 10c3 is 105, I think. Oh, sorry, 120.
120 it is coming.
120, yeah, 120. So we have 130 as the total number of points. So this satisfies our inequality, and hence 10 is the minimum number of white points that we require. So this was a very simple problem actually. You just had to think like. So does anyone have any doubts regarding this?
No.
Okay, nice. So we solved 2 RMO problems in the span of like 30 minutes. Beautiful. So one of you had doubts regarding that double counting proof that we did the previous class. So we'll do it again.
Yeah,
now.
could you please repeat that 2 and C
Yeah,
and 1?
Yeah. So we were trying to prove that 2ncn is equal to nc0 square plus nc1 square up to ncn square.
Dada, the board is very lazy. Now
Your video
went off.
Dada, actually in between I couldn't hear anything. Can you repeat that previous sum?
No.
Dada, your video went off. due to low bandwidth.
Is it better now?
We can see the video, but it's a bit hazy.
No, it is still a bit hazy.
Okay, let me just do this one. For you. Okay, can you guys see now?
Better.
Okay, it's better. So we had to prove that 2ncn is equal to 2nc0 square plus nc1 square up to ncn square. So one way of looking at this is, suppose you have n distinct black balls and n distinct white balls. So in how many ways could you choose n balls from these 2n balls? So obviously say that the answer is 2ncn. That's one way of looking at it. But in a double counting argument, we'll look at this from a different perspective.
Dada, your video
So-
went off.
Okay. I hope you can see now.
Yeah, but it's easy.
Okay, so I'll just say what it is. So take the first case as case 1. Okay, let's call it case 0. So case 0 is we choose n black balls and 0 white balls. So in how many ways could we do this? We could do this in ncn into nc0 way, right? Now let's take a general case. Suppose case k. Case k is we choose n minus k black balls and k white balls. I mean, how many ways could we do this? We could do this in nc n minus k into nck way. Now we know that nc n minus k is equal to nck. So we could basically write this as nck whole square. Now if we took all the cases from case 0, case 1, case 2 up to case n, that we are selecting n black balls, 0 white balls, we are selecting n minus 1 black balls, 1 white ball, up to 0 black balls, n white balls. So if we add up all these cases, we get summation of nck whole square. So we get nc0 square plus nc1 square up to ncn square. So basically this and this are the same thing.
Suppose not for exactly RMO, these proofs come. So what is a better way? This means ball type way or the algebraic way better to prove them?
Either of them are fine actually. When you're double counting, you need to use both of these ways actually to prove the equality. That is. Okay, so we'll show this with an example. So in the handout we gave this sum. Okay, I'll just try to screen share. Okay, so can you guys see problem 4.4?
The whole part is not visible.
Now it's visible.
It's
Yeah,
visible,
now
right?
it's okay.
Okay, 4.4. China Hong Kong match again.
Dada, how long the class will last?
Bhaiya, can you now explain it? Hello? Hello?
I don't think we are audible to him.
I think we should write in the group.
Ahir Dada is not in the meeting anymore.
Sahib bhai, are you there?
Should we leave the meeting?